Hello everyone, my name is Julien Villa-Massone. I founded Dynamic Orbits 4 years ago, and we do simulation of constellations in low Earth orbit, Starlink, Kuiper, OneWeb, for the benefit of the SATCOM industry. We're like a consulting company. And I'm going to talk about MarsLink, which is a project to connect the Earth and Mars with about 1 gigabit per second to start, and maybe more in the future. So my goal is to give you an overview of the MarsLink constellation, the way that we see it, and then a few findings of, based on simulation, what we found that's interesting. So this is the agenda for the presentation today. First, why did we do this, and why is this constellation interesting? The Earth-Mars communication paradigm. So what is it today? What is it going to be in the future? What are the different design options? We have one design for 1 gigabit per second, and we want to share this information with you, and then look at the cost. The cost is really important, because if the cost is too high, it's not going to happen. So 1 year ago, 2024, there was a tweet talking about a NASA RFP for a project. NASA was trying to get the industry to give project ideas to connect the Earth and Mars. And NASA's data rate requirement was 4 megabit per second. So we have Blue Origin, Lockheed, and SpaceX that responded, and they got awarded the right to actually do the project, which is just a study, really. But only SpaceX had a design that is really for 1 gigabit per second. And so the rest of the presentation is what I think SpaceX design will be. Okay. Okay, so until now, the communications were in space were pretty slow, and like on Earth, the data rate increases over time. So on the orange line is the internet speed on Earth, and we see that it's been increasing, of course, with the fiber delivering high speeds. And with space, it's the same, where with the initial missions, the speed is pretty slow. Of course, it depends on the distance. But we try to get the speeds to increase, so we think there will be a similar trend. The problem, of course, is the inverse square law. That means that the further you go and the less data rate you can get. But we have here a few points of the Psyche mission, which shows that it's actually true, and the further you go and the less bandwidth you actually get. So the problem is that Earth and Mars are not always like near each other, of course. And as you go far, well, the data rate goes from 1 gigabit per second to 1 megabit per second at a distance that is sort of similar to the Earth-Mars distance in average. So you need some relays, and then you can keep a high speed as the distance is actually reduced between relays. Of course, you can't place relays there, because then there's orbits, and they move all the time. So that's the problem we're trying to solve here. It's a heliocentric constellation. So the satellites orbit not the Earth, but they orbit the Sun. And the goal is to reduce the distance between relays, but also to have a low cost, as low, it's still expensive, but low cost thanks to the economies of scale, like Starlink or like Kuiper, you do a lot of similar satellites, thousands of them, and so the unit cost is a lot less. So you get to a sweet spot. So here are some design options. So first of all, looking at the sort of orbital tools, like I call them, you have here, this is the Earth, and there, this is Mars. So you have a few circular rings here. They're just rings that are perfectly circular around the Sun. You actually have 3 of them, one here, and one here. And then you have here a partial Earth ring. So that's satellites that are on the same orbit as the Earth. And then you have a partial Mars ring, which is some satellites on the same ring as Mars. You also have here an eccentric ring, which is the same as a circular ring. It's just orbiting the Sun, but it's eccentric rather than being circular. And each point here is actually one satellite. So there's a bunch of satellites here. There's less density here. It's just an example to tell you like the different words that I'm using. And all these links are just like links between different satellites. So that's an entire network here connecting one planet to another. So here are the different designs. One of them is the classic Hohmann design, like I call it, because it's really the Earth orbit, the Mars orbit, and then the design transfer orbit. The Hohmann transfer orbit. And so here, if you zoom in, there will be a lot of small satellites all around here. And you can see here some of the links when the satellites get close enough. So the data goes from this planet this way, and then that way through the Hohmann transfer orbit, and then again this way to Mars. And then there's also this other path that is available. We have the circular ring design. This is just a bunch of concentrating rings. And there's less density here, so each ring has less satellites than on this one. But there's a lot of parallel paths. So this is a serial option, this is a parallel option, and that's just 3 eccentric rings instead of just 1 here. So it's a hybrid solution. Those are general designs, and our study shows that this one has more potential. Now let's look in detail. This is just a zoomed in version to show you the actual satellites here. Each point between links is a satellite. So there's less satellites density here, and there's more satellite density on these ones, just to give you an idea. Now, if we take the parallel one, the concentric design, if you unfold it and make it just square to make it easier to understand, the Earth is here, that's Mars, and then there's a bunch of satellites lined up, and you need to pass all the data through those 2 paths, and then it's a multi-path network that then congregates back to Mars. This is how it works. Now that's the simulation. This is available at marslink.io. It's free. It's just the computer simulation, and you can change. Here are some parameters. Here we have the circular ring design, but you can change, how many circles you want, the density of satellites, and then there will be the output on the right side here, giving you the actual megabit per second or gigabit per second that you obtain. It's the sum of all the links, of the capacity of all the links that is calculated. So here, I think I'm working with the eccentric rings to look at different design options. So if you want to see how we can get 1 gigabit per second from Earth to Mars, you can go and try it by yourself and see what your design would be. I'm just using this to then do the model, well, the analysis, the study. Okay, so here's just comparing those 3 options. We have the base case, the classic Hohmann transfer scenario. We have the eccentric rings and the circular rings. This one is more expensive without adding much more value. This one is a little more expensive, but there's a lot of benefits. The latency is always optimal. It's always the best latency you can get, whereas this one has a really bad latency because it has to do a lot of distance. There's a very poor resilience to failure here, whereas here, since there's many paths, there's a high resilience to failure. Here you can deploy the satellites at any point in time, whereas here you have to wait to be at the right spot to launch, or at least to send the satellites. And then there's a real benefit here, which is if you have a spacecraft in transit from Earth to Mars or back, here you can connect these spacecraft. If the travel is 6 months and there's humans in there, well, you want them to be able to communicate back with a high speed, and that's possible here at any point, anywhere between Earth and Mars. Whereas for this is not possible. So here's my design for 1 gigabit per second. First of all, we have an uncertainty as we model this, something we just don't know. It's like how cheap and how efficient can we make the laser terminals on board the satellites. We expect 4 terminals per satellite. And there's things we can do to increase the performance from today's technology. And those things are, more power, different modulation, a more sensitive receiver. There's things that can be done to improve the performance while not increasing the cost too much. So I'm not going to go in detail, excuse me, and just to let you know, there's a way to improve the performance. So today, the baseline is really the SpaceX ISL, inter-satellite link used in the Starlink constellation. Then we have a TSAT device that is 70 times more performant, so more bandwidth, more data rate. and the Psyche emission is like 90,000 times. So it's possible to have a really high performance laser. But this thing is really expensive. It couldn't be implemented at like 1,000 satellite scale. So we need to find the sweet spot between the performance and the cost. This is what makes this constellation possible. So here we take a few, this is a sensitivity analysis, okay? That's a model, the model running with different scenarios, different number of rings, so 2 rings, 4 rings, 6 rings, 8 rings, and different number of satellites inside each ring to achieve a certain megabit per second inside the ring. But the important point here is that since we don't know what the laser technology will be in 5 years at the sweet spot cost, we have different improvement factors. And we don't know if it's going to be around 64 or around 4,000. So we take different scenarios and just have a look. And so, yeah, if we have 2 rings and 50 megabit per second, then we have 2,200 satellites, 84 megabit per second. That's not good enough. We want 1 gigabit. So here in orange, we have the different options that deliver about 1 gigabit per second. So I'm taking this one as an example. It's 1,700 satellites. For memory, the Starlink constellation is about 10,000 right now. So it's definitely doable in terms of like how many satellites. And the bandwidth would be, or the data rate would be 1 gigabit per second in this model. So this is the model that I just selected to give you an idea of how it looks. So we have like all these rings, all the satellites here communicating. And what is red here is where there's data flowing. What is white is there's no data because those satellites are not used at the moment. So the Earth is here, and Mars is, I don't know, somewhere here. And the data flows not just on one path, but uses many paths to aggregate many megabit per second. So maybe there's 4 megabit per second on one link, 10 megabits on another one, and in total it's 1 gigabit. Just the latency, maybe you might be interested in what is it. So when they're close enough, well, the closest possible is between 6.6 minutes at the best, and the average is 16 minutes latency. When it's the worst case, then it's 30 minutes minimum, and the average is 37. Now, let's look at the cost. That's an important part. So we also have, if you click on our simulation on the deployment report, this is not to scare you, it's just to give you an idea of what's going on behind in the back end of the program. We simulate the launch of all the satellites, basically. So that's the launch, Starship launching, going to orbit, separating, in-orbit refueling, blah, blah, blah. And that's all the in-orbit refuelers that launch, and they all come back and land. That's to reduce the cost, of course. And once we simulate this for all the rings, we get a report that looks like this, which is how much fuel we need, how many satellites we need, how many laser terminals we need. And the same with the financial summary, which is in millions of dollars. The total is like $11.7 billion for this constellation we just saw. That's based on our assumptions, of course, which might not be correct. It's just a model. But I think the assumptions are, plausible. And so that's the same table as we saw before, but now we're looking at the cost. And that shows that this constellation for 1 gigabit per second is 11.7 billion. But if the laser technology improves, then we need less satellites. So we can have something that costs 5 or 6 or 7 billion. So it seems, of course, very expensive, but it seems in the realm of what is possible. Because if you want to have like a village on Mars, like humans living there, a base, having only like 1 megabit per second seems to be insufficient, especially if you have hundreds of people and maybe hundreds and thousands of robots. You need to be able to monitor what they're doing and give them instructions. And if you're an astronaut there, you want to be able to chat with your loved ones, not FaceTime, but like send videos and access data and things like that. So it seems that it's plausible that some companies might do this at some point. I don't know, or governments. So the key findings are the circular orbits is the best configuration. It can serve in-transit spacecraft, which is really important, because you don't want those people to be disconnected during 6 months. You need 4 laser ports per satellite. That's important because Starlink has 3 laser ports per satellite, but this is different. There will be a trade-off between the number of satellites you want to put inside each ring and the number of rings. It's a balance. You can increase one, but that decreases the value of having more satellites on the rings. It's really important to improve the performance of the laser terminals and to have them mass manufactured. That is the key to solving this problem. But we know that the custom laser terminals already exceed the performance required. And so it's like 1,000 to 4,000 satellites. That's what it takes, really. So it's really doable. 5 to 30 billion, but probably in the 5 to 10 billion would enable a Mars colony. Thank you very much.
Thank you. We have time for questions. Yes.
Thank you. It's an amazing concept. Looks really, really interesting. It is a station-keeping nightmare.
Yes.
For sure. So when we talk about if you compare Starlink with such a constellation and think of the lifetime of the average Starlink satellite, you are going down a rabbit's hole. That aside, your competition would be a 50-meter solid dish on the surface of Mars that is reflecting a Goldstone antenna. Have you compared that? What type of data volumes you would be able to transfer?
So first of all, with the first question on the lifespan of satellites, so Starlink is 5 years. We expect this to be more, maybe 8 or 10, but I don't think it would be more than that, personally. But
you have running costs all the time.
yeah, you do. But just like Starlink, you know, if they have 12,000 satellites, they do renew them every 5 years. So that's their business, anyways. You know, it's how they operate, and I assume it will be similar here. Otherwise, you cannot have a low cost. But that's just my assumption, and it might be completely wrong. But going back to your second question, I think you said you have a giant dish on Mars sending data directly to Earth, yeah?
Yes.
Okay.
And maybe one relay satellite in between to have no blackout.
Or one relay to avoid the sun. Yeah, that's another option. We have not studied that. I don't expect SpaceX to implement that, but I think it would be worse to do it. I just haven't done it. But if you want to help with modeling this one, then we can have a comparison. It would be very interesting.
Yes.
Yeah. I was wondering if you've thought about ways that you would clean up the satellite.
Can you please speak up? Because we have.
Oh yeah.
Ways to clean up the satellites.
Yes, because I'm worried about like a new kind of space junk. Because I can't think of a way that you could conceivably like get these back. And I'm also concerned about solar storms because Starlinks are somewhat protected by Earth's electromagnetic protection. But I can't see that happening out in space. So thought about it.
Yeah, so this simulation is very crude in the sense that it's only looking at orbital locations. We're not looking even at like station keeping, because those like they will drift and stuff. I don't know how much fuel is required to keep them in position. So it's a very crude model. And for your question, which is space debris, really, I don't expect anybody to go and recover the satellites, and I don't expect that you can like send them to the sun. It would take way too much delta V. So I think they just stay there and drift, and that's it. But space is so large, like even around Earth, there's already a lot of space. But in this area, it's so large, it's impossible to.
But I think that's also the type of thinking that got us to the space junk
True.
scenario in the beginning.
So I think you're recommending that there should be a deorbit mechanism. So there would need to be to have a lot of fuel to be able to go into the sun or come back to Earth or something like that. But yeah, this is not modeled.